Today we're gonna make our player turn left and right. And the way we're gonna do that is by using a mathematical concept called quaternions. So let's jump right in. Before we program this new behavior in our player controller script, it might be helpful to think about what is it that we're trying to accomplish first. What I mean to say is that we shouldn't program blindly and hope everything works out. We should instead think abstractly and systematically about the logic that's gonna govern the player's behavior. This way, we could write clean and optimized code that's easy to develop and manage. Let me show you what I mean. In here, I've created this simple 2D diagram that's supposed to be a test case for all the possible ways our player can move in the scene. The first thing I did was impose a global coordinate system in the scene. So there is no from my side it's west and from your side it's east. West is west, north is north, and east is east. So the directions are absolute. And we're not gonna consider the south direction because our player is gonna always be running forward. Left of the diagram, I've created a table that's gonna let me know the player's future direction and rotation based on his current direction and the adjacent bridge segment ahead of him. So in the first row of the table, we have the player's current direction, which is either north, east, or west, denoted by N, E, and W, respectively. And on the first column, we have the next bridge segment type, be it straight, right corner, or left corner, denoted by S, R, and L, in that order. So I'm gonna populate the cells of the table appropriately as I run this test case simulation of our game. Let's begin. If the player's current direction is north and the next segment is straight, then he should remain in the north direction with no change to his rotation. And if the player's current direction is north and the next segment is a right corner, then his new direction should be east and he should turn by 90 degrees. So now, given that the player's current direction has become east and the next segment is straight, then his new direction is also east with no change to his previous rotation. And if the player's current direction is east and there is a left corner segment ahead of him, then his new direction would revert back to north and his rotation gets changed back to 0 degrees. If the player's current direction is north and the next segment is a left corner, then his new direction is west and his new rotation is minus 90 degrees or 270 degrees. And if the player's current direction is west and the next segment he encounters is straight, then both his direction and rotation should remain unchanged. Finally, if the player's current direction is west and the next segment is a right corner, then his next direction should be north with a rotation of 0 degrees. You might ask yourself, what about these two cases? What happens when the player's direction is east and the next segment is a right corner? Well, we're not gonna allow that to happen because in that case the player would be running backward and losing distance. Same goes for the case when he's facing west and sees a left corner. Now this has turned into a lookup table for the player's direction and rotation values given all the possible combinations between his current direction and the segment type. Our job now is to turn the values in this table into C# code in our player controller script in Unity. And it seems like an easy thing to do now because we understand how the logic works on a detailed level. It's difficult to code something when you don't know how it works. But before we program the left and right corner behavior of our player, let's see how Unity receives input from the user in the Unity manual. Simply search for input, go to this page, click on Input Manager, go to Key Code or go to this link directly. And right here in this example script, it's showing us that we need to write an if statement that checks for the key press and then does something based on that press. In our case, it's turning either left or right. And below, it's showing us a list of all the Unity key codes that are mapped to the physical keys on your keyboard. We'll use the F key to make the player turn left and the G key to make him turn right. You might be thinking that using the left and right arrows might be a better choice, but we are actually going to use the left and right arrows for the horizontal translational movement of our player. And I know that our goal is to ultimately have gesture swipes and not keyboard keys, and we'll do that in a future designated tutorial. It's actually not that hard to implement. But right now we'll consider the F and G keys to be like left and right swipes. Okay, so open up the player controller script in Visual Studio. First, let's create a new type variable called an enumerator that, you guessed it, enumerates item in a collection. So type enum in direction. Open up a pair of curly brackets and list the elements that we want this enumerator to enumerate, which is the player's directions. So type the first element, which is north, then put a comma to separate the elements, and then add the second element, which is east, and finally west. Put a semicolon. So now we have an enumerator that can enumerate our player's direction. And if we hover over any of the elements in the collection, we can see that the enumerator is assigning a number to it, i.e. it's counting them. North is 0, east is 1, and west is 2. And let's do a meaningless step of making our enumeration list vertical, just because I like seeing them listed vertically. You don't have to do that though. Now let's create a variable of that newly created type called player direction, and initialize it at the start to north. Let's create another variable of the same type and name it player next direction and also initialize it to north. This is because when our game starts, our player is facing in the north direction by default. Now let's go to the player logic function and write a simple if statement that checks if the user has pressed the G key in the keyboard just like we saw in the manual. So if a G key press is detected, then what? Well, we said that we wanted the player to turn right when the user hits G. So let's write a switch statement that's gonna check the player's current direction and then manipulate his behavior based on each case. So type switch, open a pair of parentheses, and we wanna evaluate the player direction variable. And by the way, switch statements are very similar to if statements. In fact, anything that we can do with a switch statement, we can do with an if statement and vice versa. But since we already have an if statement here, I do want to nest another if statement inside of it. That would take away from the code's readability. Now let's break down each of the cases for the player direction. Type case in direction dot north colon. So if the player's current direction is north and the user hits G on his keyboard, then change the player's next direction to east. Also, change the player's rotation by changing the rotation values in the transform component of this game object, which is the player's game object. So type this dot transform dot rotation equals quaternions, and quaternions are the mathematical way that Unity uses to rotate 3D objects like our player. You don't need to know the math behind quaternions, you just need to know how to use them in Unity. And I've attached a page from the Unity manual that goes over how to use the quaternion class in Unity, so be sure to check it. We're gonna use a method in the quaternion class called Euler to rotate our player. So type .Euler, and now we have what's called the Euler angles, which is the kind that you probably are familiar with. Open a pair of parentheses. Now we wanna rotate our player by 90 degrees around the y-axis. So type 0 in the x-axis, 90 in the y-axis, and 0 in the z-axis. Put a semicolon. Now create a new line and type break semicolon. This break keyword means do not check other cases if this case is true. So exit the switch statement after this break keyword. And we want that, right? There is no need to check other cases because our player can only be in one direction at a time. Okay, so let's continue to the other case. When can the player turn right? Well, if you remember from our table, we said that the player can only turn right if he's running north or west. So let's code the player's behavior for when the G key is pressed and he's running west. Let's just write another case for the west direction. And now the player's next direction after he turns right is north, and his rotation is 0 degrees. This does it for the right direction. Now lucky for us, the code is very similar for when the player turns left. So let's make our if statement checks for the other condition, which is if the user presses F on their keyboard. Type else F. So if the first condition is not true, then check for this second condition, which is input dot get key down, open a pair of parentheses, key code dot F. And let's copy and paste our code from the first condition and adjust what needs to be adjusted. We said that the player could only turn left if his current direction is either north or east. So keep the first case as north and change the next direction to west if the player is running north and turns left for when the user presses the F key and his rotation is minus 90 degrees around the y-axis. Also change the other case to east. And we actually don't need to change these lines because our player should turn north if the F key is pressed while he's running east. So now let's read this if statement from the start. If a G key press is detected, then check the player's current direction. If it happens to be north, then set his next direction to east and change his rotation by 90 degrees around the y-axis. Also, do not check the other case for when the player could be running west. Else if the first condition is not true, then check for the second condition for when an F key is pressed on the keyboard. In which case, check for the player's current direction. If it happens to be east, then change his next direction to north and change his rotation to 0 degrees. Now exit this if statement. I hope this was a good explanation for this bit of code. It's really important to understand what is it that you're coding so that you know how to fix your game if you encounter a problem. So now let's exit this if statement and set the player's current direction equal to the now updated player's next direction. Now I like to express my angles in 3 digits just because they look cooler, so I'm gonna do that now. Now we have set the direction and rotation of the player accounting for all cases. We now need to tell it to start moving in said direction. So let's write a string of if statements that are gonna check for the player's current direction and move him accordingly. So if the player's current direction is north, notice that I have put 2 equal signs. This means in C# these 2 quantities are equivalent. So if these 2 quantities are equal to each other, i.e. the player's current direction is north, then the player vector is equal to the unit forward vector. So this is the same as new vector 3 0 0 1. But I've written it this way because it's easier. and we'll multiply it by the updated and incremented speed from this line times time.delta time. We can see the Visual Studio is telling us that this statement is the same as vector3 0 0 1 if we hover over it. Now we will do the same for the other two directions. We will just adjust the respective unit vectors. For the east direction, we need a right unit vector. And for the west direction, we need a left unit vector. The benefit of these if statements is that now we have isolated both the vertical and horizontal component of our player movement so that we could adjust them independently from the player's forward speed. Otherwise, the player will be pulled down way too quickly when he's jumping up, or he'll move left and right far quicker than we would like him to. Okay, let's dictate the horizontal movement to our player below in the script. We'll write a switch statement that checks for the player's current direction. If the player's current direction is north, then we want him to translate along the x-axis. So let's adjust the x component of our player vector variable. Type input dot get axis raw, open a pair of parentheses, a pair of quotation marks, horizontal. So this here creates what's called a virtual horizontal axis that allows the game object, i.e. our player, to translate left and right on the fixed horizontal axis. It's basically like the analog stick on your Xbox or PlayStation controller that you use to adjust the camera, and it's automatically mapped to the left and right arrow keys on your keyboard. That's why we chose the F and G keys for the left and right turns. Later we'll configure this virtual horizontal axis to the user's phone accelerometer, so the player in the game will translate left and right if the user tilts their phone left and right, just like in the real game. Now let's code the behavior of the other two directions, but this time we'll be manipulating the z-axis instead because the player will be running on the x-axis. So let's consider the east direction, and we'll adjust the z component of the player's movement and fix it to a horizontal virtual axis that he could translate on, just like with the previous case. But now the positive x direction is left of the player, so we need to put a negative sign so that we could basically mirror the axis. Finally, let's code the translational movement of our player when he's running in the west direction. Again, we'll be playing with the z component of our player vector variable. So let's just set it equal to the virtual horizontal axis. And here we don't need to flip the sign because the positive x direction is right of the player, which is the default case. Also, let's just section off this block of code by inserting a comment that explains what this block of code does. This way our code becomes much neater. Now let's just do one final thing. Let's go up here and create a float that we are gonna call smooth factor and set it equal to 10. Now let's go to each instance of the virtual axis in our script and multiply it by this smooth factor float, and also multiply it by time.delta time. The reason we do this is because the virtual axis values are raw, so we need a way to smooth them out. This way it's in sync with the player's current speed. Let's repeat the same process for the other two instances. Now let's save the changes we've made to our script and give our game a run in the editor. And let's hope that we haven't made any mistakes here in our code. Just one quick thing, we want to temporarily change the start speed of our player so that we could better observe and test his movement on the plane we've created from the previous tutorial. I want to make it 1 unit per second. Now let's go back to the editor. I think it might be better to have a temporary 2D top view of our game, simply because it's the best way to test our newly programmed behavior. So reset the camera transform, elevate it by 20 units so that we could see the whole quad, rotate the camera by 90 degrees around the x-axis, bring it forward by 5 units. This looks good. Save and hit play. Our player is moving north now, and if I hit F, he turns left. If I hit F again, nothing happens, which is what we want. And if I hit G, he turns right to the north. And if I hit G again, he turns right to the east. And if I hit G again, nothing happens. And if I hit F, he turns to the north. So, it looks like we got it. Our player is moving as expected. Oh, let's also test the translational movement of our player. Hit play again. Now I'm gonna hold the left and right arrows. That looks good. Let's turn left and hold the arrows again. Okay, this seems right. Finally, let's turn north and then east. It looks like it's working properly. And I know that we can't have the player turn left and right willy-nilly, so we obviously gonna have to fix that in a future tutorial, so that he could only turn right if he's running on a right corner bridge segment, and only turn left if he's running on a left corner bridge segment. Okay, let's go back to the player control script and change the player start speed back to 10 units per second, and save once more. And I want to section off the code for the vertical movement before the start of the next tutorial by inserting a comment here. Now believe it or not, we've written about 70% of the player's behavior script. The only thing left to do is the animation and collision detection for when the player dies, which are actually pretty easy to do. So the hardest part is over. Congrats for making it this far. This marks the end of this tutorial. I hope that you've learned a lot from it. In the next tutorial, we're gonna write our camera logic script so that it follows the player, just like in the real game, and we'll be one step closer to completing our TempleRun clone game. Thank you.